Great. So thank you, Julie, again. So I'm Daniel Hopp. I'm working at UNCTAD, also the organizers of this session on nowcasting. So I'm going to be talking today about the use of long short-term memory neural networks in the context of economic nowcasting. So the agenda. So first, I'm going to give a little bit of background information on economic nowcasting in general. So I'm sure many people in this session have some kind of idea what nowcasting is, just to be sure, a little bit of context. Then I'm going to talk about the types of issues that nowcasting type of data issues it frequently faces. Then I will speak briefly on artificial neural networks in general, and then more specifically on the long short-term memory network and their relevance to the nowcasting problem in the economic sphere. And then finally, I will talk about the empirical analysis that we performed at UNCTAD to validate its performance versus the dynamic factor model, which is what we currently use for our nowcast at UNCTAD, and which is a very common and popular methodology in the realm of economic nowcasting. So first, a little bit of background on the field. So the term nowcasting is a portmanteau of now and forecast, and was originally used in the meteorology sphere to refer to the prediction of the weather in the very near future based on its current state. So this terminology was extrapolated to economics, where it refers to the estimation of either the real or the near real-time value of a target variable or a target series using more timely available indicators. So by way of example, GDP is a good one. So GDP is a number that is generally published with a long lag or a long delay. And we won't actually have the final figure for GDP for a period or a quarter until many months after that quarter has finished. So that makes it a really good candidate for nowcasting. And it's one of the more commonly nowcasted macroeconomic variables. So though GDP itself is published with a significant lag, there are other indicators of GDP and of the economy in general, which are published much more quickly than that figure. So that's information like consumer surveys, purchasing manager indices, data on marine traffic and trade. So we can use all of these more timely available indicators to somehow estimate the value of GDP well before the actual value is published. And so that's called a nowcast because we may be nowcasting, let's say, the second quarter of 2020, even after the second quarter has passed, because the data takes so long to be published that it's still a useful exercise to try to predict or say what Q2 GDP was, even after the period has passed. So in this domain, there's a couple of different data characteristics that arise when you're trying to solve this type of problem. So the first is the mixed frequency of data that you're working with. So for instance, we may be trying to nowcast a quarterly variable using monthly variables, or we may be trying to nowcast an annual variable using a mixture of monthly and quarterly variables. So any methodology that you employ for nowcasting has to deal with this type of mixed frequency in the data somehow. A second commonly arising issue is that the explanatory variables in your model will generally be published with very different publication schedules. So it's not like on this day, all the data for this month is published and you now have complete data for that month. It's that, this particular series will be published just 1 month afterwards, and the other ones might take 3 months. So you have a phenomenon called ragged edges commonly in the space. So that's where you will have different latest data available depending on the economic series and the publication schedule for that series. So that's another characteristic that any methodology has to somehow be robust to. And then another common issue is the recursive dimensionality. So this is where we may have relatively many more variables in our model than we do observations. So if we're nowcasting a quarterly or an annual variable, we may not have that much history or that many observations of the target series, but we may have many more potential explanatory variables. So this is a common, you end up with problems of collinearity, etc. So again, the methodology for nowcasting should be somehow robust to this characteristic. There are, of course, other data issues that are relevant to nowcasting, but these are just three of the kind of most prominent or most important. And again, any methodology for nowcasting should somehow have provisions for dealing with these characteristics. So that brings us to the artificial neural network and how this can be used in this context. So first, I'll give a little bit of background on the artificial neural networks in general and kind of the concept behind them. By this point, many of you may have a little bit of background information on them, but if not, this is a very quick overview. So in a generalized sense, neural networks are composed of layers of nodes, or neurons, that's where the terminology comes from, which at their core, they transform input data via weights to obtain output. So if we take this diagram here, I'm not sure if you can see my cursor, but if we take the first row of this blue diagram, the leftmost layer represents the initial data that we're working with, our input data. So if we were nowcasting GDP, this would be our economic survey data, our marine traffic data, etc. The data would then flow through the network, be multiplied by the weights, so this W1, W2, etc., and then combined on this hidden layer, so the second layer. And these weights are initially randomized. And then once you move to the next layer in the network, the outputs are run through a nonlinear activation function. And this is an important characteristic of neural networks, which enables them to find nonlinear relationships in data. I think it's the source of a lot of their power. And then you can continue this process with as many layers as training or as need specifies. And then eventually you'll end up with your output or your prediction. You then run this prediction through a cost function. So this can be something like mean absolute error, root mean square error for a regression problem, like we're dealing with most of the time in economic nowcasting. And then you can use this cost function to perform gradient descent and update the weights of the network in the direction of minimizing this cost function. So you're tuning the network to minimize your error. And then once those weights have been updated by following the gradient by some small amount called the learning rate, you run the data through again with a new weight, you obtain a new output, and you run through the cost function again, and you repeat this process many, many times. So, and then once you've minimized the error, the network is considered trained or fixed, and then you can begin using that network for inference. So running new data through the trained network, which at its core is these weights, and then you can have inference and predictions on new data. So this is the traditional feed-forward artificial neural network architecture. And these are super powerful for a lot of different applications, but they do not have a time component. So it's usually used for independent observations. So things like photos, etc. So in the nowcasting context, of course, the time element is very important. Most of the data is time series, and we're trying to predict the latest iteration in a time series. So we need some way to incorporate time into the architecture. So the recurrent neural network is an adaptation of the feed-forward network, which introduces a temporal aspect to the networks. However, they come with their own set of issues that make them a little bit not so well suited to the nowcasting context. The biggest one is they suffer from something called vanishing gradients or exploding gradients. Basically, they have a very short memory, and that limits their usefulness in the nowcasting context. So that is where the long short-term memory network comes into play. And this builds off the recurrent neural network, however, introduces something called a forget gate, which is a very important component which allows the gradients that I talked about earlier to flow through the network unchanged, and thus makes the network have a much longer memory, being able to deal with much longer time series. And that is ultimately what makes them so useful for use in a nowcasting context. So LSTMs traditionally have been used or are very popular in natural language processing, speech recognition, other types of things where there's a temporal component. However, they have not been used that much in the economic context. There are a couple studies on it, but it's largely a new domain for the methodology. So then how do the LSTMs then, how do they stack up in this nowcasting context? How are they able to handle these issues that I mentioned earlier? So the networks can deal with mixed frequency data by being able to learn the complex nonlinear relationships in the data via that nonlinear activation function I mentioned earlier, which means that you can put in mixed frequency data with something like the mean for missing values, and the network can learn to kind of disregard those intermediate values and focus on the quarterly values, say, and skip the in-between months. The ragged edges that I mentioned earlier can in turn be addressed with various methods. So in the empirical analysis that I'll talk about a bit afterwards, we use the mean and an ARMA model. So basically you're estimating what the next value is and using that as an input to the model. So this is not particular to the LSTM architecture. It can be treated as sort of a hyperparameter, and various methods can be tested with it. But again, in our empirical analysis, the mean and ARMA were both well-performing in that role. And then finally, the networks can handle huge numbers of input variables. So in this plot here, I have how the performance time or the model estimation time scales as the number of input features increases. So here, the red line on the bottom, we have the LSTM neural network, and we see that as we add more and more features to our model, the model actually is hardly scaling at all, the model estimation time. Whereas I have two different implementations of the dynamic factor model, and they both are scaling exponentially. So as we get up to more and more input features, their performance gets longer and longer to estimate a new model. This depends on the implementation of the dynamic factor model you're using. There are some that can handle many more input variables, but right now what we're using at UNCTAD, these are the limitations that we're up against. So that's good in theory, but then how do we validate this in practice? So to validate it, we carried out an analysis comparing the LSTM's performance in nowcasting to the dynamic factor models that we currently use. So we had three different target variables, which were global merchandise exports expressed in values, merchandise exports expressed in volumes, and then finally global services exports. So to test the two different methodologies' performance in this exercise, we had a large pool of potential explanatory variables, which we then trained both DFM and LSTM models on over a training period from 2005 to 2016, and a test or evaluation set from 2016 to 2019. Then for robustness, we took 100 random samples of between 5 and 20 of this pool of variables and trained LSTM and DFM models on those identical variable sets, and then assessed that performance on the test set, so this 2016 to 2019 period. So the analysis was performed on 100 different subsamples of independent variables for robustness. So if we were to only test this on one particular set of independent variables, either methodology could be superior in that context just based on random chance. So by sampling 100 different random samples of independent variables, we can have a much more robust idea of, on the aggregate, how are the methodologies performing. This is an interesting question of variable selection, which actually Fernando will touch on in the next presentation. So keep it in mind, and you'll learn a bit more in the next presentation. So these are the results of the analysis. So in the columns, we have our two different performance metrics. So the mean absolute error on the left, and then root mean square on the right. And then in the rows, we have different data vintages. So ranging from 2 months before the target period, when not very much data is available, to 2 months after the target period, when the majority of data for that period has been released. So the reason that we test on different data vintages is that over the course of a nowcast, the methodology should be able to have good predictions early in the cycle when there's not much information available, as well as later on. So a methodology that performs very well 2 months after, when your data is almost complete, may be very useful then, but 2 months before, when not much data is available, if it performs very terribly, that's not necessarily a very effective nowcasting methodology in the holistic sense. So then what these distributions are showing is the 3 different target variables. So the red is the export values, the green is volumes, and then the blue is services. So basically, these are the distribution of the 100 random subsamples of independent variables, and then plotted the LSTM error as a proportion of the dynamic factor model's error. So the black can be kind of taken as the baseline, our current outputs. So if we have distributions centered around the black line, that's indicating that the 2 methodologies have similar predictive performance. So if we look at global services in root mean square error, this blue distribution is centered around the black line, which means that more or less we're having pretty similar predictive performance. However, we see that most of the distributions, in fact, all of them except this blue one, are centered to the left of the blue line, which indicates that on average, the LSTM is having significantly less error than the DFM. So those are, of course, promising empirical results, but even leaving aside that performance, we have other characteristics of the models that we can compare. So on the empirical predictive performance front, there should, of course, be more testing and validation on different time periods, on different target variables, just to ensure the robustness of those results. Maybe there's something special about merchandise exports and services where the LSTM is better suited. So that should be further validated. But there are some characteristics which are independent predictive performance that we can still compare and contrast between the 2 methodologies. So some pros that we saw in a previous slide was that the LSTM can handle many more input variables than the dynamic factor model implementation that we are currently using at UNCTAD. And then on top of that, that the methodology does not run into any estimation or calculation problems, which the DFM sometimes can do due to uninvertible matrices, etc. And then on top of that, it's simpler to add new frequencies, data frequencies to the long short-term memory network. Can handle theoretically daily data mixed with yearly data, mixed with even theoretically hourly data. Of course, that needs to be tested, but in theory, there's no limitation to that, where the DFM requires a little bit more tuning or tweaking to accept other frequencies. And then so on the cons front, we have the stochastic nature of both neural networks in general, but also, of course, of the LSTM network. So this comes from what I mentioned in my neural network slide, where the initialization of the weights is initially random, and that's just to provide a starting point for the network. So this little stochasticness means that 2 models trained on the exact same data will give 2 different predictions. So this can be mitigated a bit by training in many networks and taking their average or their median and other more complex ensembling methodologies, but it is a factor, the stochastic nature of neural networks. And then next is the lack of interpretability in parameters and lack of inference as to what is driving the decisions or the changes in the network's outputs. This again is a problem common to all neural networks, but there's a rich field on how to get interpretability out of them. But in the LSTM nowcasting context, that's an area for further research to try to get a measure of interpretability from these models. And then there's a couple of things where whether it's a pro or con kind of depends. So one is the estimation time of the 2 methods. This is highly dependent on the hyperparameters of the LSTM and on various EM convergence of the dynamic factor model. So you have a little bit of variability in which one is actually faster in estimating a model. But generally speaking, in the empirical analysis that I did, training one single LSTM model is almost always faster than training one single dynamic factor model. That advantage kind of goes away a bit when you have to train multiple models to get a little bit less of that stochastic element to the LSTM's outputs, but nevertheless, one single LSTM generally will be trained faster than one single dynamic factor model. And then finally, the LSTM takes many more hyperparameters than a dynamic factor model. So this is a pro in the sense that the performance of the model can be improved and tweaked, but it's a con in the sense that that takes a lot more effort to properly leverage on the side of the analyst or the statistician who is doing the analysis. So in conclusion, the research on the LSTM has shown it to be a promising methodology in the nowcasting space with desirable characteristics which might help expand applications for nowcasting, expand its application from just the very classical macroeconomic variables to some of these newer SDG indicators. But of course, more research needs to be performed. And on this final slide, which I assume will be made available via the ISI portal, I put some additional resources, including links to the Python and R libraries that was created alongside this research so that anybody could use these models for their nowcasting applications, as well as links to the UNCTAD research paper, which is detailing this methodology in much more detail in this presentation. And then finally, the UNCTAD research paper on the dynamic factor models that we currently use and which was contrasted with the performance of the LSTM. So that's it for me. Thanks a lot. Let's see if there were any questions in the, I don't know if I can see the chat while I'm sharing. Let me stop sharing and check. Okay, I don't see anything there. But if any participants have any questions or anyone else? Okay, so
Daniel, sorry.
Yes, please.
I don't know a lot about neural networks, but I was thinking, you mentioned that different models learn in a different way. In econometrics, you define criteria to see what is better. Do you have something similar to compare models and how they perform?
So do you mean something beyond the so I had been using the empirical performance on these test series and just root mean square and mean absolute error on the in comparison to other methodologies. I am working now on some more research using the development of the forecasts over time as another metric for their usefulness in the nowcasting context. But for now, it's mostly around empirical performance on these series. I don't know if that answers your question or if
yes,
there's other metrics.